Every star you have ever seen in the night sky is dying, not slowly fading in some poetic, meaningless way, but undergoing one of the most violent and transformative processes the universe has ever produced. And the way each one ends determines whether it goes out quietly, leaving behind a glowing shell of color that expands across light years of space, or violently, leaving behind a city-sized ball of matter so dense that a teaspoon of it weighs as much as a mountain range, or a hole in the very fabric of space-time that swallows light itself and never, under any physical law we know of, lets it go. This video covers all of that in full. What happens inside stars as they run out of fuel, how their deaths play out across millions and billions of years, how those deaths literally built the atoms in your body, and why none of us, not a single atom anywhere in you, would exist without them. Hit like, drop a comment telling me where you are watching from and what you are doing right now, because I genuinely love seeing who finds these videos and where in the world they find you. Subscribe if you are new. Now let us get into it. Think about what that means for a moment. Every light in the night sky above you is the product of a nuclear fire that has been burning for millions or billions of years. Each one is fighting gravity every second of every day. Each one will eventually lose that fight. And the way it loses, the specific physics of how it fails and what it leaves behind, turns out to matter enormously for the history of everything else in the universe, including the history of you. Stars are not just light sources. They are the universe's primary method for processing hydrogen and helium, the only elements that existed after the Big Bang, into every other element in existence. They are the factories that built the periodic table, and they only release those products when they die. You cannot have the elements without the deaths. You cannot have rocky planets without the elements. You cannot have life without rocky planets. Every link in that chain goes through stellar death. This is the story of that death, all of it. Section 1. What a star actually is, and why balance is everything. To understand how stars die, you first have to understand what keeps them alive in the first place, because the death of a star is not some separate event that comes along at the end. The death is really just the moment when two great opposing forces that have been locked in a stalemate for millions or billions of years finally tip out of balance for good. And once that balance breaks, it breaks with extraordinary speed, and the consequences ripple outward across light years of space. A star begins its life inside a nebula. This is the name astronomers give to vast clouds of gas and dust scattered throughout galaxies. These clouds are mostly hydrogen, the simplest and most abundant element in the universe, left over from the Big Bang itself. They are cold, with temperatures only a few tens of degrees above absolute zero. They are diffuse, spread across regions that might span dozens or even hundreds of light years. From a distance, a nebula looks like a smear of faint color against the darkness, something gentle and static, a painting rather than a process. That impression is completely deceiving. Nebulae are the birthplaces of stars, and within them, gravity is always working. For long stretches of cosmic time, these clouds drift gently through the interstellar medium, disturbed only occasionally by passing gravitational influences, collisions with other clouds, or the shockwave propagating outward from a nearby stellar explosion. But gravity is patient. Gravity never switches off. Slight variations in density within a cloud, regions where the gas is fractionally denser than its surroundings, mean that some areas pull in surrounding material just a little faster. As mass accumulates at those denser points, their gravitational attraction increases, drawing in more material from further away, which increases their gravity further still. It is a runaway process, slow at first, then faster again, and over millions of years, a region of the cloud begins to collapse inward on itself. This collapsing cloud fragment is called a protostar. As material falls inward, gravitational potential energy converts to thermal energy, the same basic conversion that heats air when you compress it rapidly in a bicycle pump, but happening on a cosmic scale. The core temperature climbs from the few tens of degrees Kelvin of the original molecular cloud, through hundreds, then thousands, then hundreds of thousands, then millions of degrees. The pressure builds. Competing effects slow the collapse. The cloud fragments into multiple pieces. Rotation distributes material into a flattened disk surrounding the forming star. Outgoing thermal pressure pushes back against gravity from within. For a period, the protostar is a hot, still collapsing, violent young object surrounded by an infalling accretion disk of gas and dust, blasting out powerful jets of material along its polar axes that carve tunnels through the surrounding cloud and can extend for light years on either side of the protostar, their presence betraying a new star forming long before that star becomes visible. And then, at a critical core temperature of around 10 million degrees Celsius, something extraordinary happens that changes the nature of the entire object permanently and irreversibly. Protons, the nuclei of hydrogen atoms stripped of their electrons by the extreme heat, start colliding at speeds high enough to overcome the electromagnetic repulsion between them and fuse together. 4 protons combine through a chain of reactions to produce one helium nucleus, releasing a burst of energy in the form of photons and heat. The mass of 4 hydrogen nuclei is slightly more than the mass of one helium nucleus, and that tiny mass difference gets converted to energy according to Einstein's famous equation E equals mc squared. For each individual reaction, the energy released is small by everyday standards. But a star performs this reaction in numbers that are genuinely difficult to comprehend. The Sun alone converts approximately 4 million tons of mass into pure energy every single second, and has been doing so continuously for 4.5 billion years. This is nuclear fusion, and it is the engine that powers every star in the universe. Every photon of sunlight that has ever touched your skin, every unit of heat that has ever warmed you on a summer afternoon, originated as the energy from a fusion reaction deep in the Sun's core. That energy did not travel directly from the core to your skin. A photon produced in the core as a gamma ray gets absorbed almost immediately by the surrounding dense plasma and then re-emitted in a random direction. This absorption and re-emission happens countless millions of times over a journey through the solar interior that might take tens of thousands to 100,000 years. By the time the energy finally escapes the solar surface as an ordinary photon of visible light, that photon races the 8-minute journey across the solar system to Earth. But its origin was a nuclear reaction in a fire burning at 15 million degrees. The energy released by fusion radiates outward from the core, and that outward radiation pressure pushes against the inward pull of gravity. When these two forces reach equilibrium, when the outward push of radiation exactly balances the inward pull of gravity at every layer in the star, the collapse stops and the star settles into a state astronomers call hydrostatic equilibrium. The star is now on the main sequence, the long, stable middle phase of its life, burning hydrogen steadily, holding itself up against collapse, shining. Our Sun has been in this state for about 4.5 billion years. It burns hydrogen into helium at its core at an almost unimaginable rate, converting approximately 600 million tons of hydrogen into helium every single second. 600 million tons every second for 4.5 billion years. And yet the Sun contains so much hydrogen, roughly 70% of its total mass, which amounts to approximately 2 times 10 to the power of 30 kilograms, that it can sustain this rate of burning for roughly another 5 billion years before the supply in the core starts to meaningfully deplete. But here is the central organizing principle of stellar physics, and it cannot be overstated. The mass of a star determines virtually everything about how it lives and how it dies. Mass determines how hot the core burns, how fast the hydrogen fuel depletes, how long the star spends on the main sequence, how dramatically it changes in its later phases, which nuclear burning stages it passes through, and ultimately what it leaves behind. Everything flows from mass. The reason mass has such overwhelming influence comes back to hydrostatic equilibrium. A more massive star has more gravity pressing inward on its core. To counterbalance that extra gravity with outward radiation pressure, the core must burn hotter and faster, releasing more energy per unit time. The luminosity of a star scales roughly with the third or fourth power of its mass, meaning that even modest increases in mass produce dramatic increases in energy output. A star twice as massive as the Sun is not twice as luminous. It is roughly 10 to 16 times as luminous, depending on where exactly on the main sequence you look. A star 10 times as massive as the Sun burns perhaps 10,000 times as brightly, and luminosity is what determines how fast the fuel burns. A star 10 times the mass of the Sun has roughly 10 times as much hydrogen fuel, but burns that fuel roughly 10,000 times as fast. The result is a lifespan measured not in billions of years, but in tens of millions. A star 40 or 50 times the mass of the Sun exhausts its core hydrogen in only a few million years, a time span shorter than the gap between the extinctions of the non-avian dinosaurs and today. These most massive stars are born, shine with an almost incomprehensible brilliance, and die before the universe has had time to blink. At the other end of the scale, the dimmest red dwarf stars burn so slowly and so efficiently that they can sustain hydrogen burning for trillions of years. A red dwarf with about a tenth of the Sun's mass is fully convective, circulating its hydrogen continuously throughout its entire volume, rather than allowing a helium-rich core to accumulate at the center. It burns through virtually all of its hydrogen, not just the central supply, and does so at such a leisurely rate that the process could continue for 10 trillion years or more. The universe is currently only about 13.8 billion years old. Not a single red dwarf that has ever formed has run out of fuel. Every red dwarf in the history of the cosmos is still on the main sequence right now, without exception. They will outlast every other type of star by factors of hundreds or thousands, burning on in an increasingly dark and quiet universe long after everything brighter has burned out. There is one more thing worth establishing before we move on from the basics of what a star is, and it concerns time. The timescales involved in stellar physics are so far outside human experience that they require a deliberate effort to hold in mind. The Sun has been burning for 4.6 billion years. In that time, human civilization as we understand it, everything from the first cities to the internet, has lasted maybe 10,000 years, which is about 0.02% of the Sun's current age. The Sun's expected remaining main sequence lifetime of 5 billion years is so much longer than all of recorded human history combined that the comparison is meaningless in any intuitive sense. And yet on stellar scales, the Sun is a medium-lived star. The most massive stars burn out in millions of years. Red dwarfs will burn for trillions. The range of stellar lifetimes spans 12 or more orders of magnitude. That range is part of what makes stellar physics so rich, and it is part of what makes stellar death so varied. A star dying after 10 million years dies differently, leaves behind different products, and has a different impact on its surroundings than a star dying after 10 billion years. Mass sets the pace, and the pace sets everything else. Mass sorts all stars into two great categories of fate. Stars below roughly 8 times the mass of the Sun, the overwhelming majority of all stars, including our own Sun, follow a path toward a quiet, slow, luminous death. Stars above that 8 solar mass threshold follow a path toward a catastrophically violent death that reshapes everything around them and creates objects whose properties sit at the extreme edge of what physics can describe. Both paths are extraordinary. Both deserve to be understood completely. Section 2. The first warning signs, when the balance begins to shift. The first warning signs that a star is approaching the end of its main sequence life come not from any change visible on the surface, but from the slow, invisible shifts happening deep in the stellar core. Stars keep their dying hidden for a long time. A star can be undergoing dramatic internal restructuring, while its outer appearance changes only gradually over millions of years. The drama is buried under hundreds of thousands of kilometers of dense plasma, far beyond any direct observation. For billions of years, a Sun-like star fuses hydrogen into helium in its central core. This is the process that defines the main sequence, and during this phase, the star is remarkably stable, a model of long-term constancy. But the helium produced by this fusion accumulates in the core, gradually displacing the hydrogen. The core is not static during this process. It slowly contracts under its own weight as the hydrogen is depleted, and this gradual contraction causes the core to heat up over time. As the core grows hotter, the fusion reactions run faster, and the star brightens slowly but measurably over billions of years. The Sun today is about 30% more luminous than it was when it formed 4.6 billion years ago, a difference that would have profound consequences for planetary climates over geological timescales. The early Earth was warmer than a 30% dimmer Sun should have allowed. a puzzle known as the faint young sun paradox, whose resolution involves combinations of greenhouse gases, cloud cover, and other atmospheric effects. The decisive transition comes when the hydrogen in the core runs low enough that fusion there begins to slow and then stop. This is not a sudden event. It happens gradually as the hydrogen is depleted, the fusion slowing progressively as the hydrogen fraction falls. Eventually, the core hydrogen is effectively exhausted and fusion in the core ceases. At that moment, the radiation pressure holding the core up against gravity disappears. Gravity, which has been counterbalanced for billions of years, begins to win in the core. The helium core contracts. But this contraction, rather than being a simple collapse, becomes the trigger for the next phase of the star's life. As the helium core contracts under gravity, it heats up through the conversion of gravitational potential energy to thermal energy. The increasing temperature ignites hydrogen fusion in a shell of material surrounding the inert helium core, a shell that was previously too cool for fusion. This shell burning of hydrogen releases more energy than the original core burning did, because the shell is under higher pressure from the overlying stellar material. All that extra energy pushes the outer layers of the star outward. The star begins to swell, first by a modest amount, then progressively more dramatically as more and more energy is poured into the outer envelope. This is the subgiant phase, which lasts hundreds of millions of years as the star adjusts to its new internal configuration. Eventually, the swelling becomes radical. The outer layers expand by factors of tens, then hundreds, cooling as they expand and shifting in color from yellow-white through orange toward deep red. The star has entered the red giant phase, one of the most visually recognizable stages in all of stellar evolution. For the Sun, this transformation lies about 5 billion years in the future. When it arrives, the Sun will swell to a size that dwarfs anything in the inner solar system. Its radius will grow to perhaps 200 or more times its current value, and the surface of the expanding Sun may reach or exceed the current orbit of Earth. Whether Earth survives this expansion physically depends on subtle details of how quickly the Sun loses mass during the giant phase, because mass loss weakens the gravitational force binding Earth to the Sun and causes Earth's orbit to expand outward. Some models predict Earth migrates outward fast enough to avoid engulfment. Others predict it spirals into the solar atmosphere and vaporizes. What is certain is that Earth will have been a dead, sterile rock for billions of years before this happens. The oceans boiled off and the atmosphere stripped long before the Sun reaches its full red giant size. For the most massive stars, the swelling process is far more extreme. They become red supergiants, some of the largest physical objects known to exist. Betelgeuse, which we will explore in detail later, has a radius between 640 and 764 solar radii. Placed at the center of our solar system, its photosphere would extend past the orbits of Mercury, Venus, Earth, and Mars, swallowing those planets entirely. Jupiter's orbit would lie near its surface. There are other red supergiants even larger. Phi Canis Majoris may have a radius exceeding 1,400 solar radii, a sphere so enormous that light traveling at 300,000 kilometers per second would take more than 8 hours to cross it. These are real objects, made of ordinary hydrogen and helium, governed by the same physics as the Sun, simply scaled up to proportions that resist intuitive comprehension. Section 3. The Quiet Death. How stars like our Sun spend their last billion years. For stars below roughly 8 solar masses, the red giant phase is the beginning of the final chapter. That chapter, drawn out over hundreds of millions of years, ends not in violence but in something far more beautiful: the slow, luminous release of a star's outer layers into surrounding space, leaving behind a glowing record of the star's existence and a slowly cooling stellar remnant that will outlast the current age of the universe by a wide margin. Inside the red giant, the helium core keeps contracting and heating as the hydrogen-burning shell above it grows outward from the center. The core temperature climbs steadily. For a star with a mass between roughly half and about 8 solar masses, the critical temperature of approximately 100 million degrees Celsius is eventually reached in the core, and helium ignites. In Sun-like stars with masses between roughly half and 2 solar masses, this ignition does not arrive gradually. it arrives suddenly in what astronomers call the helium flash. By the time the helium core reaches ignition temperature, it has entered a quantum mechanical state called electron degeneracy. In this state, the pressure holding the core up against gravity no longer comes from thermal energy in the ordinary sense, but from the quantum mechanical resistance of electrons to occupying the same state simultaneously, a consequence of the Pauli exclusion principle, one of the foundational rules of quantum mechanics. In an ordinary gas, fusion provides its own thermostat. More fusion releases heat, which causes the gas to expand, which lowers the temperature and pressure, which slows the fusion back down. The system self-regulates. But in a degenerate gas, this thermostat is broken. Adding heat to a degenerate gas does not cause it to expand in the normal way. So when helium fusion ignites in the degenerate core, the heat produced cannot expand the core. It simply raises the temperature. Higher temperature drives higher fusion rates. More heat raises the temperature further still. A brief runaway begins. This runaway, the helium flash, releases an astounding amount of energy. Some estimates put it at something comparable to the luminosity of the entire Milky Way galaxy for a brief period. But essentially none of this energy reaches the stellar surface. It goes into lifting the degeneracy of the core, converting the electron-degenerate matter back into ordinary gas that responds thermally to temperature changes in the normal way. Once the degeneracy is lifted, the thermostat is restored, the fusion rate stabilizes, and the helium core settles into a steady burn. From the outside of the star, essentially nothing changes during the helium flash. No observable signature reaches the surface. One of the most powerful events in a star's life happens in complete internal secrecy, invisible to anyone watching from outside. After the helium flash, the star settles onto the horizontal branch, burning helium steadily in its core for tens of millions of years, fusing 3 helium nuclei into 1 carbon nucleus through the triple alpha process, and some of that carbon capturing another helium nucleus to become oxygen. The star actually shrinks somewhat from its red giant maximum during this phase. It is a period of relative stability, but it is finite. The helium in the core eventually runs low too. When the core helium is exhausted, the carbon-oxygen core contracts and heats, and now the star has 2 active burning shells surrounding the inert core, a helium burning shell, and above it, a hydrogen burning shell. This dual shell burning creates a more energetic and unstable configuration than the star has experienced before. The star re-expands, climbing to sizes even larger and luminosities even higher than during the first red giant phase. It has entered the asymptotic giant branch. An asymptotic giant branch star pulsates rhythmically, its outer layers expanding and contracting over periods of hundreds to thousands of days. The 2 burning shells interact in a complex way, with periodic thermal pulses where the helium shell ignites in a runaway flash, puffs up, and temporarily extinguishes the hydrogen shell above it before the system re-equilibrates. Between thermal pulses, convective mixing currents dredge material from deep in the star up toward the surface, bringing nuclear-processed material, including carbon and S-process heavy elements, into the outer layers where it can be carried away by the stellar wind. The mass loss rate on the asymptotic giant branch is enormous by comparison to the main sequence Sun's gentle solar wind. Where the Sun currently loses roughly 10 to the power of -14 solar masses per year, an asymptotic giant branch star can lose mass at rates approaching 10 to the power of -4 solar masses per year, 10 billion times faster. The star is dissolving itself, blowing off its outer atmosphere in waves over tens of thousands of years. By the time most of the outer envelope has been expelled, the star has contributed enormous quantities of processed material to the interstellar medium: carbon, nitrogen, oxygen, and the products of slow neutron capture nucleosynthesis. As the outer envelope thins and eventually disperses, the hot carbon-oxygen core that has been building throughout the star's late evolution becomes increasingly exposed. The surface temperature of this core can exceed 100,000 degrees Celsius, blazing with ultraviolet photons. Those ultraviolet photons stream outward into the surrounding expelled gas, ionizing the hydrogen, helium, oxygen, nitrogen, and other atoms in the expanding shell. The ionized gas glows. What we see from Earth is a planetary nebula. The name planetary nebula is a complete misnomer, the result of a historical quirk. William Herschel coined it in the 18th century because the small, round, slightly greenish objects he observed through his telescope reminded him of the telescopic disk appearance of planets he had studied. They have nothing to do with planets. A planetary nebula is the expelled outer atmosphere of a dying star, illuminated by the ultraviolet radiation of the hot stellar core being exposed at its center. The term has persisted for 2.5 centuries and will not change now. The variety of planetary nebulae in shape, structure, and chemistry is extraordinary. Some are simple, nearly spherical shells, the result of a roughly symmetric mass loss history. Others are bipolar, shaped like hourglasses or butterfly wings, their striking geometry determined by the rotation and magnetic field of the dying star, and by the presence of binary companions that shape the pattern of mass loss around the equatorial plane relative to the polar axes. Others show multiple concentric shells recording distinct episodes of mass loss separated by thousands of years, each episode leaving an expanding ring of gas that glows independently in the surrounding nebula. Still others show complex jets, knots, and filamentary structures whose detailed dynamics reflect turbulent processes in the expelling atmosphere. The Ring Nebula in Lyra, one of the most photographed objects in the amateur astronomy sky, is a glowing ring about 1 light-year across, with the exposed hot core at its center shining at about 120,000 degrees. The Helix Nebula in Aquarius is the nearest planetary nebula to Earth at roughly 650 light-years, and when photographed, its apparent angular size on the sky is about half the diameter of the full moon, vast and structurally rich. The Butterfly Nebula in Scorpius shows a dramatic bipolar structure with polar jets extending from the central star along the rotation axis. The Cat's Eye Nebula in Draco shows an intricate nested structure of 11 or more rings and other features reflecting a complex mass loss history. Each planetary nebula is a unique record of a specific stellar death, and no two are alike. The colors in planetary nebulae are real physical signatures of ionized atoms emitting light at specific wavelengths. The blue-green glow that dominates many planetary nebulae in visual wavelength photographs is forbidden line emission from doubly ionized oxygen atoms that have lost 2 electrons, emitting at wavelengths of 496 and 501 nanometers. Red and pink regions are hydrogen recombination emission at the H-alpha wavelength of 656 nanometers. Oranges and golds appear from combinations of ionized nitrogen and sulfur. Different regions of the nebula glow in different colors depending on the temperature, density, and composition of the gas at that location. Looking at a planetary nebula in detail, you are reading a chemical map of the star's expelled atmosphere. At the center of every planetary nebula is the white dwarf. This is the exposed core of the original star, compressed into an object roughly the size of Earth and containing roughly half the original stellar mass. The mean density of a white dwarf is about 1,000,000 times the density of water. A teaspoon of white dwarf material, brought to Earth's surface, would weigh several tons. What holds it up against its own gravity is not nuclear fusion, which has ceased entirely, but electron degeneracy pressure. The electrons packed into the white dwarf resist further compression because quantum mechanics forbids 2 electrons from occupying the same quantum state simultaneously. This pressure is not temperature dependent. The white dwarf could cool to absolute zero and would not collapse further. White dwarfs generate no energy. They simply radiate away the stored heat of their entire previous history, cooling slowly and dimming over billions of years. A freshly formed white dwarf can have a surface temperature exceeding 100,000 degrees Celsius. Over hundreds of millions of years, it cools. Over billions of years, it dims. The eventual endpoint, a cold, inert, dark object the size of a planet, is called a black dwarf. The problem is that cooling a white dwarf all the way to a black dwarf takes far longer than the current age of the universe. Not one black dwarf exists anywhere in the observable universe. Every white dwarf ever formed is still glowing, still cooling, still on its incredibly long journey toward an endpoint the universe has not yet been around long enough to produce. The white dwarf that forms at the center of a planetary nebula is not just a stellar remnant in some passive sense. It has its own extraordinary story. Freshly formed white dwarfs are among the hottest stellar surfaces in the universe, radiating almost entirely in the ultraviolet and extreme ultraviolet. As they cool over millions of years, they shift through the range of wavelengths visible to human eyes, glowing white, then yellow, then orange, then red, as they slowly lose the heat accumulated over billions of years of nuclear burning. By the time a white dwarf has cooled to temperatures comparable to the Sun's surface, it has been cooling for billions of years already. White dwarfs also sometimes have extraordinary second acts. When a white dwarf exists in a close binary system with a companion star, it can accrete material from the companion as the companion evolves and its outer layers expand toward the white dwarf. Hydrogen accumulates on the white dwarf's surface until the temperature and pressure ignite a thermonuclear runaway in the accreted layer. This explosive burning is so violent that it blasts the accumulated material off the white dwarf's surface in a nova, a brief dramatic brightening visible across the galaxy. Novae recur as accretion continues and another layer of hydrogen accumulates and ignites. They are the universe's way of letting white dwarfs have brief, spectacular second lives without destroying them. If the accretion continues long enough and the white dwarf grows in mass toward the Chandrasekhar limit, a different and far more violent outcome becomes possible: a Type Ia supernova, in which the entire white dwarf is consumed in a thermonuclear explosion rather than just the surface layer. Type Ia supernovae are cosmologically important because their peak luminosities are nearly uniform, making them usable as distance indicators across the observable universe. It was the observation of Type Ia supernovae in distant galaxies in the late 1990s that revealed the accelerating expansion of the universe and led to the concept of dark energy, one of the most important cosmological discoveries of the modern era. So white dwarfs are not simply the dead ends of stellar evolution, they are participants in binary interactions that produce novae and potentially Type Ia supernovae, and Type Ia supernovae are, through the observations they enabled, part of the story of how we came to understand the ultimate fate of the universe itself. About 6% of all stars in the Sun's neighborhood are white dwarfs, the remnants of stars that lived and died. The nearest one, Sirius B, orbits the brightest star in our sky at a distance of 8.6 light-years. Its existence predicted from gravitational perturbations in Sirius's motion before it was directly observed in 1862. Section 4. The Cosmic Recycling. How dying stars seed the galaxy. The material expelled by a dying star does not vanish into nothingness. It enters the interstellar medium, the vast diffuse reservoir of gas and dust between stars, and it participates actively in the processes that form the next generation of stars and planetary systems. Every dying star is simultaneously an ending and a contribution to the next beginning. The interstellar medium is not a passive background. It is a dynamic, chemically evolving system continuously being enriched and stirred by stellar deaths. The universe began with an almost laughably simple chemical composition. In the first minutes after the Big Bang, a process called Big Bang nucleosynthesis assembled the lightest nuclei: hydrogen, helium, and tiny amounts of lithium and beryllium. That was the entire chemical inventory of the primordial universe. Roughly 75% hydrogen by mass, 25% helium, and negligible traces of everything else. No carbon, no oxygen, no nitrogen, no silicon, no iron, no gold, nothing complex. The entire periodic table beyond beryllium did not exist. The first generation of stars formed from this near-pristine gas. They lived, burned, and died, returning processed material to the interstellar medium. The second generation of stars formed from gas, slightly enriched by those deaths. Each subsequent generation added to the chemical complexity of the interstellar medium, inheriting the accumulated nucleosynthetic output of all previous generations and adding to it. Our Sun, formed 4.6 billion years ago, incorporated material from many previous stellar generations, which is why its spectrum reveals dozens of elements heavier than helium, whose abundances could only have been built up through billions of years of stellar nucleosynthesis and recycling. This chemical evolution of galaxies is directly observable. Stars in the outer halo of the Milky Way, which formed in the earliest epochs of galactic history, are systematically poor in elements heavier than helium compared to younger stars in the disk and central bulge, which formed more recently from more enriched gas. The most ancient stars identified have iron abundances 1,000 to 10,000 times lower than the Sun. By studying these ancient stars, astronomers can directly probe the nucleosynthesis products of the very first stellar generations. When a Sun-like star dies and disperses its outer layers as a planetary nebula, the primary chemical contributions to the interstellar medium are carbon, nitrogen, and oxygen. The slow neutron capture process occurring during helium shell-burning pulses on the asymptotic giant branch also produces and distributes heavier elements, including strontium, barium, lead, and bismuth. These S-process contributions from low-mass dying stars account for a large fraction of the heavier-than-iron element abundances in the solar system. The chemical enrichment of the galaxy by stellar death is not a uniform or smooth process. It is patchy, episodic, and uneven, with different regions of the galaxy enriched to different degrees at different times by the deaths of different types of stars. Massive stars explode as core collapse supernovae within millions of years of formation and enrich their immediate surroundings with oxygen, silicon, calcium, and iron in a geologically brief burst. Low-mass stars take billions of years to evolve to the planetary nebula stage and enrich the interstellar medium with carbon, nitrogen, and S-process heavy elements on a slow, steady, diffuse timescale. Neutron star mergers enrich with R-process heavy elements on timescales set by the time required for two neutron stars to spiral together and merge, which for tight orbits can be millions of years, but for wider orbits can be billions of years. This means that different regions of the galaxy that formed their stellar populations at different cosmic times and under different conditions have different chemical signatures. Old, metal-poor stars in the galactic halo reflect the enrichment by massive stars only, since low-mass AGB stars and neutron star mergers had not yet had time to contribute when those stars formed. Younger stars in the galactic disk reflect the accumulated contributions of all three main enrichment channels operating over more than 10 billion years of galactic history. When astronomers study the chemical abundances of individual stars in detail, they can essentially read the chemical history of the galaxy in the stellar spectra. The ratio of carbon to oxygen tells you about the relative contributions of AGB stars and massive stars. The ratio of barium to europium tells you about the relative contributions of the S process and the R process, and therefore about the history of AGB stellar deaths versus neutron star mergers in the star's birth environment. The detailed elemental abundance patterns of a star are a chemical fossil record of the galaxy's history at the time and place where that star formed. In recent years, the field of galactic archaeology has developed powerful techniques for using these chemical fossils to reconstruct the past of the Milky Way, identifying stars born in now disrupted satellite galaxies that were subsequently absorbed into the Milky Way, tracing the history of star formation across different galactic components, and probing the rates and sites of different nucleosynthesis processes as a function of cosmic time. The deaths of stars across billions of years have left a detailed chemical record in the spectra of living stars, and reading that record is one of the most powerful tools modern astrophysics has for understanding the history of our galaxy. The atoms that make up your body have all passed through at least one stellar interior. The carbon in your DNA was made in a stellar helium burning zone. The oxygen in your lungs was made in stellar burning and distributed by stellar death. The nitrogen in your amino acids was processed through stellar hydrogen burning. The calcium in your bones was forged in oxygen burning in a massive star. All of it was expelled into the interstellar medium by stellar death, mixed into the gas clouds of the early solar system, and eventually incorporated into Earth's rock and ocean chemistry, from which biology later assembled it into you. Section 5. The violent death. What happens inside a dying massive star? For stars exceeding about 8 times the mass of the Sun, the story runs on a completely different track, and the endpoint is not a beautiful nebula and a quietly cooling white dwarf, but one of the most energetically extreme events the universe is capable of producing, a core collapse supernova. The divergence from the low-mass path happens after helium burning. A low-mass star exhausts its helium, builds a carbon-oxygen core, and lacks the gravity to compress that core to the temperatures needed for carbon fusion. Carbon is the end of the nuclear road for low-mass stars. But a high-mass star has more overlying mass pressing down on the core, compressing it to higher temperatures and pressures. And in this compressed environment, carbon ignites. Once carbon ignites, what follows is a cascade of successively higher nuclear burning stages, each happening faster than the last, each building heavier elements, until the entire structure races toward an inevitable catastrophic conclusion. Carbon burns at roughly 500 million to 1 billion degrees Celsius, producing neon, sodium, magnesium, and some aluminum. In a star like Betelgeuse, this phase lasts roughly 1,000 years. When the carbon runs low, the core contracts and heats further, and neon ignites at around 1.2 billion degrees, producing oxygen and magnesium. Neon burning lasts only about a year in a massive star, then oxygen burning at 1.5 to 2 billion degrees, producing silicon, sulfur, argon, calcium, chlorine, potassium, and other elements in that region of the periodic table. Oxygen burning lasts a few months. And finally, silicon burning at around 3 billion degrees, where a complex equilibrium of photodisintegration and reassembly reactions builds up the iron peak elements: iron, nickel, cobalt, chromium, and titanium. Silicon burning, the final nuclear burning stage, lasts only days. Consider what this timeline means. A massive star spends millions of years on the main sequence burning hydrogen, hundreds of thousands of years burning helium, roughly 1,000 years burning carbon, about a year burning neon, a few months burning oxygen, days burning silicon. The star is accelerating toward its death through a series of burning stages that get shorter and shorter, each fuel reserve depleted faster than the last. If you compressed the full nuclear history of a massive star into a single hour, the star would spend most of that hour burning hydrogen, a few minutes on helium, a few seconds on carbon, and then the last fractions of a second on neon, oxygen, and silicon combined, and then it would die. By the time silicon burning is underway in the core, the star has developed a complex layered interior called the onion skin structure, an iron core at the center, surrounded by a silicon burning shell, an oxygen burning shell, a neon shell, a carbon shell, a helium shell, and the hydrogen burning envelope at the outermost extent of the nuclear processing zones. Each shell occupies a different temperature and pressure environment, and is consuming different fuel at a different rate. The surface of the star, a bloated red supergiant, gives no indication of this extraordinary internal complexity. It looks stable. It looks like any other red supergiant. The countdown is completely hidden. Then the silicon burning stops, and the iron core simply grows as silicon burning around it adds more iron to its mass. Iron cannot yield energy by being fused into heavier elements. Iron sits at the absolute minimum of the nuclear binding energy curve. Every other element, fused or split, either gains or loses energy in the process, but iron is at the bottom. You have to put energy in to do anything with iron. So the iron core is inert, it just accumulates. The Chandrasekhar limit, approximately 1.4 solar masses, is the maximum mass that electron degeneracy pressure can support against gravity. When the iron core reaches this mass, electron degeneracy pressure can no longer hold it up. The collapse begins. And from this moment, events unfold at a pace that defies any everyday comparison. In approximately 1/4 of a second, the iron core, previously roughly the size of Earth, compresses down to a sphere about 20 to 30 kilometers across. The infalling material reaches velocities that are significant fractions of the speed of light. Temperatures in the collapsing core reach hundreds of billions of degrees. The extreme photons present at these temperatures begin photodisintegrating the iron nuclei, blasting them apart back into individual protons and neutrons, undoing billions of years of nuclear construction in an instant. This photodisintegration costs energy, accelerating the collapse further. Free electrons and protons are crushed together to form neutrons, releasing floods of electron neutrinos. When the collapsing core reaches nuclear density, roughly 4 times 10 to the power of 17 kilograms per cubic meter, the strong nuclear force resists further compression. Nuclear matter is effectively incompressible at this density. The infall stops suddenly, and the core rebounds. A shockwave propagates outward through the still infalling outer core material. But the shockwave stalls. It loses energy continuously to the inward falling matter, to the photodisintegration of ion nuclei it encounters as it moves out, to neutrino losses. Within a fraction of a second of forming, the shockwave sits at roughly 100 to 200 kilometers from the center, unable to push outward through the infalling material, its energy balanced against the ram pressure of the infall. What revives it is neutrinos. The proto-neutron star forming at the center produces roughly 10 to the power of 58 neutrinos in the first 10 seconds of its existence, more neutrinos than the Sun will emit across its entire 10 billion year lifetime. A tiny fraction of this neutrino energy, perhaps 1 or 2%, gets deposited in the region behind the stalled shockwave. That fraction is sufficient. The neutrino-heated matter convects and bubbles, depositing energy into the shockwave, eventually restarting it. Once revived, the shockwave tears outward through the stellar envelope, accelerating into lower density outer material. The star explodes. The mechanism by which neutrinos revive the stalled shockwave in a core collapse supernova is not a simple process, and the details of how it works are still being worked out by researchers using increasingly sophisticated three-dimensional computer simulations. Early simulations in 1 or 2 dimensions, which treated the explosion as spherically symmetric, consistently failed to explode the star. The neutrino energy deposited behind the shockwave was not quite sufficient to overcome the ram pressure of the infalling material. It was only when simulations became three-dimensional, able to model the convective instabilities, turbulence, and fluid flows that develop in the region between the stalled shockwave and the neutron star, that robust explosions could be produced. The three-dimensional nature of the explosion matters enormously. In 2 dimensions, matter tends to settle into laminar flows that do not efficiently redistribute the deposited neutrino energy. In 3 dimensions, vigorous convective bubbles form, carrying neutrino-heated material from the inner region where neutrino heating is intense outward to the shockwave, and carrying cooler, denser material downward toward the neutron star, where it can absorb more neutrino energy. The turbulence in the gain region, the shell between the neutron star and the shockwave where net energy is deposited from neutrinos, acts like a stirring mechanism that significantly amplifies the efficiency of neutrino energy deposition. Additionally, a large-scale instability called the standing accretion shock instability, or SASI, develops in many simulations, producing large sloshing and spiraling motions of the stalled shock that also help drive the explosion. The asymmetries introduced by these three-dimensional effects during the explosion are one of the reasons that neutron stars are born with significant velocity kicks, often hundreds of kilometers per second, imparted to them by the asymmetric ejection of mass and neutrinos during the explosion. Pulsars have been observed moving through the galaxy at velocities consistent with having received such kicks at birth, and the distribution of pulsar velocities is consistent with what three-dimensional explosion models predict. The birth of a neutron star is violent, asymmetric, and kicks the compact remnant across the galaxy at speeds that can carry it thousands of light-years from its birthplace over millions of years. The compact remnant left by a core collapse supernova, whether neutron star or black hole, is determined by the details of the progenitor star's mass, structure, rotation, and magnetic field, and by the explosion mechanism. Not all core collapse events produce successful explosions that eject the stellar envelope. Some may result in the star's mass falling directly onto the proto-neutron star without a successful explosion, in what is sometimes called a failed supernova or direct collapse black hole. These events would produce a brief neutrino burst as the neutron star forms, and then a black hole, but no optical brightening, no supernova. Some surveys searching for red supergiants that disappear without producing a detected supernova have found candidate events consistent with failed supernovae, suggesting that a fraction of massive star deaths may be invisible in optical light, leaving behind black holes without the dramatic light show of a successful explosion. The explosion ejects most of the star's mass into space at velocities of several % of the speed of light. The total energy released is approximately 10 to the power of 44 joules, more energy than the Sun will emit over its entire 10 billion year lifetime. and roughly 99% of it leaves in neutrinos. The brilliant light of the supernova, bright enough to outshine a galaxy of hundreds of billions of stars, is only 1% of the total energy budget. Section 6. SN 1987A. The supernova that changed everything we knew. To make core collapse supernovae real rather than abstract, there is no better guide than SN 1987A, the supernova that exploded in the Large Magellanic Cloud on February 23, 1987. The Large Magellanic Cloud is a small irregular satellite galaxy of the Milky Way, visible with the naked eye from the southern hemisphere as a soft, irregular smudge of light. It sits approximately 160,000 light-years from Earth, one of our nearest galactic neighbors. When a massive star there collapsed on February 23, 1987, the light from the explosion had been traveling for 160,000 years. The event occurred tens of thousands of years before writing existed, but the universe delivered the news on a night when 3 operating neutrino detectors happened to be running and taking data. The progenitor star had been catalogued years earlier by astronomer Nicholas Sandulik in a survey of blue supergiants in the Large Magellanic Cloud. Designated Sandulik Bouch 69202, it was a blue supergiant with a mass of roughly 20 solar masses. This was immediately puzzling. The theoretical consensus held that core collapse supernovae should come from red supergiants, the natural late-stage evolutionary form of massive stars. The explosion of a blue supergiant forced significant revision of models for massive stellar evolution and is now understood as reflecting a specific evolutionary history in which the star had previously been a red supergiant and then migrated back toward higher temperatures before exploding. About 2 hours before any astronomer saw the star brighten in the sky, 3 neutrino detectors around the world simultaneously registered anomalous bursts. The Kamiokande 2 detector in Japan, a tank of 3,000 tons of ultra-pure water surrounded by 1,000 photomultiplier tubes, recorded 12 events in 13 seconds. The Irvine, Michigan Brookhaven detector in Ohio recorded 8 events in 6 seconds. The Baksan scintillator telescope in the Caucasus Mountains recorded 5 events in 9 seconds. Approximately 25 neutrinos in total, captured from a neutrino flux at Earth's surface of roughly 50 billion per square centimeter per second. The detection of 25 events from a flux of 50 billion per square centimeter per second gives a visceral sense of how rarely neutrinos interact with matter. These 25 neutrinos were among the most important particles ever detected in science. They confirmed, through direct observation for the first time, the theoretical model of core collapse supernovae. The neutrino burst arrived hours before the visible explosion because neutrinos escaped the collapsing core almost instantaneously, while the optical shockwave needed hours to traverse the stellar envelope. The total energy inferred from the detection was consistent with forming a neutron star of about 1.4 to 2 solar masses. The duration of the burst matched the predicted cooling timescale of the proto-neutron star surface. Every major prediction of the core collapse model was confirmed by those 25 particles. SN 1987A occupies a special place in the history of astronomy, not just because of what it confirmed, but because of the richness of information it continues to provide decades after the explosion. The expanding remnant has been observed by essentially every major telescope launched or built since 1987. And each new generation of instruments has revealed new details about the dynamics, chemistry, and physics of the evolving remnant. The 3 rings around SN 1987A, 1 inner ring and 2 outer rings, were a puzzle when they were first illuminated by the ultraviolet flash from the explosion shortly after it became visible. They turned out to be the product of mass loss from the progenitor star at different evolutionary stages, including a period when the star was a red supergiant and shed a large amount of material in a slow, dense wind, followed by a faster, less dense blue supergiant wind that caught up to and compressed the earlier red supergiant wind into a ring structure. The 2 outer rings may record an earlier asymmetric mass loss event or a binary interaction in the progenitor's history. Beginning in the late 1990s and continuing through the 2000s and 2010s, the supernova's blast wave began to overtake the inner circumstellar ring, heating the ring material and causing it to glow brightly in X-rays and visible light. The interaction produced dozens of bright knots and hot spots in the ring as the blast waves struck denser clumps, creating a ring of pearls of X-ray emission visible even in Hubble Space Telescope images. This interaction has been studied in unprecedented detail because the geometry and distance of SN 1987A are so well constrained, and the results have tested models of supernova remnant evolution and blast wave physics in ways that observations of more distant, older remnants cannot. The search for the neutron star in SN 1987A has been one of the long-running detective stories in modern astrophysics. Neutrino theory predicted that a neutron star formed, but the neutron star was hidden behind the expanding ejecta and the dense dust that condensed in the cooling outflow in the years after the explosion. For decades, the neutron star could not be directly detected. Different observational hints appeared over the years: indirect evidence from the energetics of the nebula, searches for pulsed emission, and X-ray observations, none of them definitive. The 2023 JAST observations finding ionized argon and sulfur consistent with illumination by a young hot neutron star were the most compelling direct evidence yet, and they fit beautifully with the theoretical expectation that a neutron star of perhaps 1.4 to 2 solar masses sits at the center of the remnant, slowly cooling and eventually becoming a pulsar detectable in radio waves as the surrounding dust and gas thins over the coming decades and centuries. In the months following the explosion, SN 1987A's light curve matched the predicted decay profile of radioactive nickel-56, decaying into cobalt-56, and then into stable iron-56. Gamma-ray telescopes detected the characteristic gamma-ray emission lines from cobalt-56 decay directly, the first ever direct measurement of freshly synthesized radioactive nuclei in a supernova. Decades of subsequent observation have provided detailed information about supernova remnant evolution, mass loss history of the progenitor star, and the interaction of the supernova shockwave with the material shed before the explosion. And in 2023, using the James Webb Space Telescope, astronomers found the most compelling evidence yet for the neutron star that formed at the core. For more than 3 decades, the neutron star was hidden behind dense dust that condensed in the cooling ejecta in the years after the explosion. Webb's mid-infrared instruments detected ionized argon and sulfur near the explosion site, ionized to states requiring a source of high-energy photons consistent with a hot young neutron star. The data strongly suggests the neutron star formed and survived. It is the youngest neutron star we know of, and as observational capabilities improve, it may become one of the most closely studied neutron stars in history. Section 7. Neutron stars, the densest objects with a surface. The neutron star left behind by a core collapse supernova is the most extreme ordinary object in the universe. Not the most extreme of all objects, since black holes transcend neutron stars in the strangeness of their space-time geometry. But neutron stars are the most extreme objects that still have physical surfaces, still have measurable radii, and still consist of matter in states that physics, however strained, can attempt to describe. A typical neutron star contains between roughly 1.4 and 2 or more solar masses compressed into a sphere about 20 kilometers across. The state of Nevada is roughly 800 kilometers wide. The island of Manhattan is about 21 kilometers long. The entire mass of the Sun compressed into something the size of Manhattan. The density is roughly 600 trillion times the density of water, approaching and exceeding the density of atomic nuclei. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. Not 1 billion grams, not 1 billion kilograms, 1 billion metric tons. Inside a neutron star, matter exists in states with no counterpart in any terrestrial laboratory. The outermost crust consists of ordinary atomic nuclei, extremely neutron-rich by ordinary standards, arranged in a crystalline lattice surrounded by a sea of degenerate electrons, somewhat resembling an exotic metal under crushing pressure. Moving deeper, the nuclei become increasingly neutron-rich until individual neutrons begin to drip out of the nuclei and flow freely through the space between them. This is the neutron drip point, a specific density threshold marking the boundary between outer and inner crust. Below this point, matter consists of exotic, unstable nuclei in a sea of free neutrons. Deeper still, the nuclei dissolve entirely. The matter becomes a continuous fluid of neutrons, with small admixtures of protons and electrons, to maintain charge neutrality. This neutron fluid may be in a state of superfluidity, a quantum mechanical phase where neutron-Cooper pairs flow without viscosity, analogous to superconductivity. If neutron superfluidity occurs in neutron star cores, and there is observational evidence from Cassiopeia A that it does, it has measurable effects on how the neutron star cools and how it responds to internal disturbances. At the very centers of the most massive neutron stars, the densities may become high enough that individual nucleons dissolve into their constituent quarks, creating a form of dense quark matter that has no terrestrial analog and whose properties are among the major unsolved problems in physics. What holds a neutron star up is neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed into the same state, combined at higher densities with the short-range repulsion of the nuclear strong force. The maximum mass a neutron star can have, the Tolman-Oppenheimer-Volkoff limit, depends on the unknown nuclear equation of state at extreme densities, but has been observationally constrained to be at least about 2 solar masses. Neutron stars are born rotating rapidly because angular momentum is conserved when the stellar core collapses from a sphere thousands of kilometers across to one about 10 kilometers in radius. Conservation of angular momentum requires the rotation rate to scale as the square of the radius ratio, which means a modest pre-collapse rotation of once per day becomes a post-collapse rotation of tens to hundreds of times per second. Their intense magnetic fields, billions to trillions of times stronger than Earth's, channel radiation outward from the magnetic poles in narrow beams. If those beams happen to sweep past Earth with each rotation, we detect precisely regular radio pulses. These are pulsars. Jocelyn Bell Burnell discovered the first pulsar in 1967 as a graduate student at Cambridge University. She noticed a source of regular, precisely repeating radio pulses, 1.337 seconds between each pulse, so regular and anomalous looking, that the research group initially called it LGM-1 for Little Green Men 1, while investigating whether it could be an artificial signal. Within months, the correct explanation was established. Anthony Hewish received the 1974 Nobel Prize in Physics for the discovery. Bell Burnell, whose observational work and analytical attention to anomalous data led directly to the find, was not included. It remains one of the most discussed exclusions in Nobel Prize history. Millisecond pulsars, spinning hundreds of times per second, are neutron stars spun up by accreting material from a binary companion star over millions of years. The fastest known rotates about 716 times per second, its surface moving at roughly 20% of the speed of light. These recycled pulsars are among the most precisely characterized objects in astrophysics, their spin rates known to 10 or more significant figures. Magnetars have magnetic fields reaching 10 to the power of 15 Gauss, a quadrillion times stronger than Earth's field. These extreme fields cause starquakes, fractures in the rigid neutron star crust that release catastrophic bursts of X-ray and gamma-ray energy. On December 27, 2004, the magnetar SGR 1180620 released a burst lasting about 1/10 of a second that produced more energy than the Sun emits in 250,000 years. This burst, from 50,000 light-years away on the far side of the Milky Way, briefly ionized Earth's upper atmosphere and was detected as a disruption to long-wave radio communications worldwide. At 1,000 light-years, such an event would have stripped away the ozone layer. Section 8. Gravitational waves and where gold comes from. Some neutron stars end up in binary systems with another neutron star. This requires a specific and somewhat improbable chain of events. Two massive stars forming in close binary orbit, the first exploding as a supernova and leaving a neutron star while the pair remains gravitationally bound, then the second star evolving and exploding in turn, again leaving the pair bound. This sequence is rare enough that only a handful of double neutron star systems are known in the Milky Way, but they are thought to be far more common than direct observation suggests. Two neutron stars locked in a binary lose orbital energy by emitting gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's 1915 general theory of relativity. As the orbit shrinks over millions or billions of years, the gravitational wave power increases. The orbit shrinks faster, and eventually, the two neutron stars merge. The first indirect evidence for gravitational wave emission from a neutron star binary came from the binary pulsar PSR B1913+16, discovered in 1974 by Russell Hulse and Joseph Taylor. The orbital period of this two-neutron star system has been decreasing at exactly the rate general relativity predicts for energy loss through gravitational wave emission. Hulse and Taylor tracked the orbit shrinking in perfect agreement with Einstein's equations for decades, winning the Nobel Prize in Physics in 1993 for this work. Direct detection of gravitational waves came from LIGO on September 14, 2015, detecting the merger of two black holes 1.3 billion light-years away. The gravitational wave signal stretched and compressed LIGO's 4-kilometer detector arms by about 1,000th the diameter of a proton. The engineering precision required to measure this was without precedent in scientific instrumentation. 2 years later came the event that directly rewrote our understanding of where the heaviest elements in the periodic table come from. On August 17, 2017, LIGO and the European Virgo detector jointly detected a gravitational wave signal lasting nearly 100 seconds, far longer than the black hole merger signals, from the merger of two neutron stars in the galaxy NGC 4993 in Hydra, about 130 million light-years away. Within 1.7 seconds of the end of the gravitational wave signal, space telescopes detected a short gamma-ray burst from the same position on the sky. This was the first multi-messenger event, the same astrophysical cataclysm detected simultaneously in gravitational waves and in light. In the following hours and days, every major telescope on Earth and in space observed a kilonova in NGC 4993, an optical transient powered by the radioactive decay of freshly synthesized heavy elements in the material ejected from the neutron star collision. The kilonova started bright blue and evolved toward red over a week, as different populations of R-process elements produced in the collision decayed and as the expanding cloud cooled. Spectroscopic analysis directly detected strontium in the ejector, a landmark identification of a specific R-process product in the debris of a neutron star collision in real time. The total mass of R-process material ejected was estimated at between 0.01 and 0.06 solar masses, several Earth masses worth of gold, platinum, and other heavy elements. Every gram of gold ever mined from the Earth was forged in a kilonova. The gold in a wedding ring, the gold in a circuit board, the platinum in a catalytic converter, the iridium in a spark plug, the uranium in a nuclear reactor. All of it was assembled in the violence of two neutron stars colliding and disrupting each other. Those neutron stars themselves only existed because massive stars had previously died in core collapse supernovae. The pathway from hydrogen and helium to a gold atom in your hand runs through, at minimum, two separate stellar deaths. The deaths of the massive stars that created the neutron stars, and then the deaths of those neutron stars in their eventual collision billions of years later. The atoms in a gold ring have had a journey. They were forged in a neutron star merger probably billions of years ago, sprayed into space in the kilonova ejector, mixed into the interstellar medium, swept up into the molecular cloud that became our solar system 4.6 billion years ago, incorporated into Earth's mantle and crust, concentrated into ore deposits, mined, refined, and shaped. Every step of that journey was necessary to bring those particular atoms from a neutron star collision to an object on your finger. Section 9. Black holes, where gravity wins without limit. For stellar cores above roughly 2 to 3 solar masses, the configuration needed for a neutron star cannot be maintained. No known force can halt the collapse. The result is a black hole, a region of spacetime from which nothing whatsoever can escape, because the geometry of spacetime inside the event horizon directs all possible futures inward. The event horizon is the defining boundary of a black hole. It is not a physical surface. There is no matter at the event horizon, no detectable boundary you could see or feel as you crossed it. It is a geometric feature of spacetime, the set of all points from which all future directed paths lead inward toward the center. none outward. Inside the event horizon, moving toward the center is as inevitable as moving forward in time. You cannot avoid it any more than you can avoid tomorrow. The size of the event horizon is given by the Schwarzschild radius, approximately 3 kilometers per solar mass of the black hole. A stellar black hole of 10 solar masses has an event horizon 30 kilometers in radius, roughly the same size as a neutron star, but with no surface, no matter, just curved spacetime. At the theoretical center, classical general relativity predicts a singularity of infinite density, widely understood as a signal that the theory is incomplete at those scales, rather than that an actual infinity exists. A complete theory of quantum gravity would be required to describe what truly happens at the center, and no such complete theory yet exists. Black holes reveal themselves through their effects on surrounding matter. In X-ray binary systems where a stellar black hole orbits a companion star, material transferred from the companion forms an accretion disk that heats to millions of degrees and emits intensely in X-rays. By measuring the orbital parameters of the companion star, the mass of the unseen compact object can be determined. When that mass exceeds about 3 solar masses, a black hole identification is secure. LIGO and Virgo have now detected gravitational waves from dozens of stellar black hole mergers, building up a catalogue of masses and merger dynamics. For a human being falling into a stellar black hole, the tidal forces, the difference in gravitational pull between one side of the body and the other, would be catastrophically large well before reaching the event horizon. The body would be stretched in the direction of infall and squeezed laterally, in a process physicists describe as spaghettification, elongated into a thin strand of matter. For a larger supermassive black hole, the tidal forces at the event horizon would be gentler, and crossing the horizon might not be immediately lethal. But inside any black hole, the eventual fate at the singularity is sealed. Stephen Hawking's 1974 theoretical prediction that black holes slowly emit thermal radiation through quantum mechanical effects near the event horizon, called Hawking radiation, implies that black holes are not permanent on sufficiently long timescales. But the Hawking temperature of a 10 solar mass black hole is about 10 to the power of -8 Kelvin, far colder than the cosmic microwave background that fills all of space. In the current universe, stellar black holes absorb far more energy from their environment than they radiate through Hawking radiation and grow rather than shrink. The evaporation timescale for a stellar black hole is roughly 10 to the power of 74 years. For all practical cosmological purposes, stellar black holes formed now are permanent. Section 10. Betelgeuse, the star, the world watched. Betelgeuse is the star the world knows is going to explode. Not imminently in any human sense, but inevitably and eventually. It is the most closely watched potential supernova in the sky, and in 2019, it did something that made people genuinely wonder whether the explosion had begun. Betelgeuse sits approximately 550 to 650 light-years from Earth, its distance uncertain due to the difficulties of measuring distances to pulsating, dust-shrouded red supergiants. It marks the right shoulder of Orion, one of the most recognized star patterns in human history across cultures. Its distinctly orange-red color, bright enough to be obvious to the naked eye, has been observed and recorded by people across the world for thousands of years. It is a red supergiant with a mass estimated between roughly 10 and 20 solar masses, a luminosity about 100,000 times that of the Sun, a surface temperature around 3,500 Kelvin, and a radius between 640 and 764 solar radii. At the center of our solar system, its surface would swallow Mercury, Venus, Earth, and Mars. Betelgeuse is a variable star, changing in brightness regularly due to pulsations of its enormous outer layers on a dominant period of roughly 400 days. These pulsations are the expected, well-understood behavior of a red supergiant. The star also shows a longer period brightness variation of roughly 2,100 days, whose origin was, until recently, unexplained. Between October 2019 and February 2020, Betelgeuse dimmed by roughly a factor of 2.5, dropping from an apparent magnitude of about 0.5 to a record minimum of about positive 1.6, the faintest it had been in at least 25 years of systematic monitoring. It dropped from one of the 10 brightest stars in the sky to outside the top 20, noticeably dimmer than Aldebaran in Taurus. Headlines worldwide asked whether Betelgeuse was about to explode. Was this the beginning of the end? Astronomers pointed out that a core collapse supernova is not preceded by weeks of gradual surface dimming detectable from Earth. Core collapse takes less than a second. The neutrino burst would arrive at Earth's detectors hours before any visible brightening. There was no physical mechanism linking surface dimming to imminent core collapse. Whatever was happening at Betelgeuse's surface was surface behavior, not a window into nuclear conditions at the core. As data accumulated, the explanation emerged. A large section of Betelgeuse's surface had ejected a substantial mass of plasma outward in what appears to have been an unusually powerful convective event. This material, cooling as it moved away from the star, condensed into dust grains a few stellar radii out. The dust cloud sat in our line of sight, blocking a significant fraction of Betelgeuse's light from reaching Earth. The dimming was an optical effect of intervening dust. By 2021, the dust had dispersed and Betelgeuse's brightness had returned to normal. In July 2025, a discovery reshaped the understanding of Betelgeuse's behavior comprehensively. A team from the Center for Astrophysics at Harvard and Smithsonian, using nearly 8 years of Hubble Space Telescope data, combined with ground-based observations, confirmed the existence of a companion star to Betelgeuse. Named Siwarha, from Arabic meaning her bracelet, this companion is a hot blue-white main-sequence star of 1.4 to 1.6 solar masses orbiting Betelgeuse, with a period of approximately 2,100 days, roughly 5.7 years. As Siwarha moves through Betelgeuse's extended outer atmosphere with each orbit, it creates a gravitational wake, a ripple of compressed gas, that modulates Betelgeuse's brightness and atmospheric behavior. The mysterious 2,100-day longer period variability that had puzzled astronomers for decades turned out to be the orbital period of Siwarha. The Great Dimming of 2019 to 2020, in retrospect, reflected the combined influence of a dust ejection event and the orbital position of Siwarha, affecting how Betelgeuse's outer atmosphere presented to our line of sight. The discovery of Siwarha shifted models of Betelgeuse's evolutionary state toward a more stable configuration than some pre-2025 analyses had suggested. The timeline to explosion, already uncertain across a range of tens of thousands to hundreds of thousands of years, was pushed further into the future. But pushed further does not mean eliminated. Betelgeuse will explode. When it does, it will be the most spectacular astronomical event in recorded human history. It will reach a brightness rivaling or exceeding the full moon, visible in broad daylight, casting faint, distinct shadows at night. Neutrino detectors around the world will catch the burst hours before the visible explosion. Modern gravitational wave detectors may detect the asymmetric collapse. Space and ground-based telescopes will record the spectral evolution from the earliest moments. The expanding remnant will be studied for centuries. When Orion rises after the event, its shape will have changed, the red shoulder star gone, replaced eventually by a faint expanding nebula, and, at its center, a neutron star. Section 11. The Forge of Everything. Nucleosynthesis in depth. Understanding nucleosynthesis, the process by which the elements were built, is understanding the most fundamental contribution that stellar death makes to the universe. Every element more complex than lithium was made in a star or in the violent aftermath of stellar death. The periodic table is a ledger of stellar history. The Big Bang produced hydrogen and helium in the ratio of roughly 3:1 by mass, with trace amounts of lithium and beryllium. The universe expanded and cooled too rapidly for reactions to proceed to heavier elements before the conditions for nuclear fusion passed. Within about 20 minutes of the Big Bang, nucleosynthesis ceased. For hundreds of millions of years afterward, the universe contained only hydrogen and helium, a vast, dark, chemically simple expanse, waiting for gravity to assemble the first stars. Hydrogen burning is the foundational nucleosynthesis process, converting hydrogen to helium in the cores of main-sequence stars across the full range of stellar masses and lifetimes. The product is helium, which accumulates and forms the raw material for subsequent burning stages. Helium burning produces carbon and oxygen through the triple alpha process. 3 helium-4 nuclei combining to form carbon-12, and some of that carbon capturing another helium-4 to form oxygen-16. Fred Hoyle predicted a specific resonance state in carbon-12 in 1953, before it had been measured, reasoning that if carbon were not produced in abundance in stars, carbon-based life could not exist, and since we are carbon-based and we exist, the resonance must be there. The resonance was measured and found at almost exactly the predicted energy. It is one of the most striking predictions in the history of astrophysics, an observer reasoning backward from the existence of life to a testable property of nuclear physics. Carbon burning, neon burning, oxygen burning, and silicon burning in massive stars build up elements across the periodic table from sodium and magnesium through the iron peak. Carbon burning at roughly 500 million to 1 billion degrees produces neon, sodium, and magnesium. Neon burning at 1.2 billion degrees produces oxygen and magnesium through photodisintegration reactions. Oxygen burning at 1.5 to 2 billion degrees produces silicon, sulfur, argon, calcium, chlorine, potassium, and neighboring elements. Silicon burning at 3 billion degrees through a quasi-statistical equilibrium of photodisintegration and recapture produces iron, nickel, cobalt, chromium, and the other iron peak elements. The elements built through these burning stages are the most abundant elements in the universe beyond hydrogen and helium, because massive stars produce them in large quantities and supernovae distribute them widely. Elements beyond iron require neutron capture rather than charged particle fusion. Adding protons to iron peak nuclei costs energy due to electromagnetic repulsion, but neutrons, with no electric charge, face no repulsion and can be added to nuclei at any energy. The slow neutron capture process, the S process, operates in the outer layers of asymptotic giant branch stars and in some regions of massive stars. The neutron density is relatively low, so captures are widely separated in time, and unstable intermediate nuclei have time to undergo beta decay between captures. The S process builds a path of nucleosynthesis along the valley of nuclear stability, reaching from the iron seed nuclei all the way to bismuth, the heaviest stable element. Elements produced primarily by the S process include strontium, barium, lanthanum, cerium, lead, and bismuth, among others. The rapid neutron capture process, the R process, requires neutron densities many orders of magnitude higher than the S process environments, so high that neutrons can be captured faster than beta decays can occur. Under these conditions, nuclei accumulate many neutrons in rapid succession, building extremely neutron-rich nuclei far from the valley of nuclear stability. When the neutron flux abates, these nuclei cascade down toward stability through chains of beta decays, producing the heavy R process elements: gold, platinum, iridium, osmium, uranium, thorium, and many others. The R process is the only pathway to produce most of the elements heavier than bismuth, and it contributes significantly to silver, europium, gadolinium, and elements in several other periodic table regions. The detection of GW 170817 and its kilonova afterglow provided the most compelling observational evidence that neutron star mergers are a major R process site. The direct identification of strontium in the kilonova spectrum, combined with the overall properties of the kilonova, pointed unambiguously to R process nucleosynthesis happening in the collision ejector. Neutron star mergers provide the right conditions. The ejected material is extremely neutron-rich, coming from disrupted neutron stars, and the neutron density during the hot, early phase after the collision is sufficient to drive rapid neutron capture at the required rate. Whether core collapse supernovae also contribute significantly to R process enrichment, particularly in the early universe before neutron star mergers were common, remains an active research area. Some astrophysicists argue that certain extreme supernovae with rapidly rotating progenitors could produce R process conditions in their neutrino-driven winds. Observations of ancient, extremely metal-poor stars in the galactic halo showing high R process element abundances suggest enrichment happened very early in galactic history, before neutron star merger rates would have been high. The full story of where the heavy elements come from is still being assembled from a growing body of gravitational wave, spectroscopic, and theoretical evidence. What is not in doubt is the fundamental conclusion: the periodic table was built in stages, by different astrophysical processes, in different types of dying stars, over the full history of the universe, from the first stellar generations to the present day. Section 12. Famous remnants, monuments to stellar death. Supernova remnants are the expanding monuments left by stellar explosions. They evolve on timescales of centuries to millennia, making them among the few astrophysical objects whose change is directly observable by human astronomers within a career, or even a lifetime. They are also chemical records of the nuclear burning that happened inside the progenitor star, preserved in the expanding shell of ejected material, and readable by the X-ray and optical and radio observations of modern telescopes. The Crab Nebula in Taurus is the most famous supernova remnant in the sky. It originated in a supernova observed in 554 CE, recorded by Chinese astronomers as a guest star bright enough to be seen in daylight for 23 days, with naked eye visibility lasting nearly 2 years. Japanese court astronomers recorded it. Arab chroniclers noted it. Petroglyphs from the American Southwest may depict it. The peak brightness was perhaps magnitude -6, comparable to the crescent moon, the most dramatic astronomical spectacle in the medieval period, witnessed by people across multiple civilizations and recorded in multiple independent traditions. Today, the Crab Nebula spans roughly 11 light-years and expands at about 1,500 kilometers per second. Its appearance varies dramatically across different wavelengths. In visible light, the nebula shows a tangle of filaments and bright knots of ejected stellar material, ionized by radiation from the central pulsar. In X-rays, the Chandra X-ray Observatory reveals a system of rings and jets centered on the Crab pulsar, structures produced by the magnetized wind of charged particles flung outward by the rotating neutron star into the surrounding nebula. In radio waves, the entire nebula glows as a non-thermal radio source, one of the brightest in the sky. The Crab pulsar at the center rotates approximately 30 times per second, emitting pulsed radiation from radio waves to gamma rays. Its spin rate is measurably decreasing as the rotating neutron star loses rotational energy to the surrounding pulsar wind. By measuring the current spin rate and its rate of decrease, astronomers calculate the rate at which rotational energy is being lost. This energy loss rate closely matches the total power needed to sustain the Crab Nebula's luminosity. The pulsar is the engine that has been keeping the Crab Nebula glowing for almost 1,000 years. Cassiopeia A is the remnant of a supernova that occurred around 1680 CE, apparently not widely noticed at the time, despite presumably reaching naked eye visibility. A possible observation by John Flamsteed is sometimes cited, though the identification remains uncertain. Cassiopeia A is one of the brightest radio sources in the sky outside the solar system, and is studied intensively at X-ray wavelengths by the Chandra X-ray Observatory. Chandra's images of Cassiopeia A have mapped the distribution of different chemical elements across the remnant in remarkable detail. Regions of the remnant enriched in oxygen correspond to what was, before the explosion, the oxygen-burning zone of the progenitor star. Regions enriched in silicon and sulfur mark the silicon-burning layer. Iron is distributed in a pattern that reflects where iron peak elements were synthesized in the explosion. The remnant is a chemical autopsy of the progenitor star's layered nuclear burning structure, preserved in expanding gas and readable 9 decades after the explosion in light that took the same 9 decades to travel to us. Cassiopeia A's central neutron star also provided the first observational evidence for neutron superfluidity inside a neutron star. X-ray monitoring over more than a decade showed the neutron star cooling faster than expected by standard thermal evolution models. The excess cooling is consistent with the onset of neutron superfluidity in the core, which releases additional neutrino cooling as neutron-Cooper pairs form and transition to the superfluid state. The temperature decline matched predictions of neutron superfluidity models, providing the first empirical evidence for this exotic quantum mechanical state of matter at nuclear densities. An astronomer on Earth measuring the temperature of a neutron star 11,000 light-years away and using that measurement to probe the quantum mechanical state of matter inside it is one of the more extraordinary things astrophysics does routinely. Other notable remnants span the history of naked-eye supernovae in recorded human history. SN 1006, whose remnant is a roughly circular X-ray and radio shell about 60 light-years across, was the supernova observed in 1006 CE, and was likely the brightest supernova in recorded human history at an estimated apparent magnitude of -7 to -9, visible in daylight for weeks, and apparently distressing to observers who had no framework for understanding a star that appeared from nowhere and outshone everything. The remnant structure suggests it originated from a Type Ia thermonuclear supernova rather than a core collapse event, the explosion of a white dwarf that had accreted enough material to exceed the Chandrasekhar limit, rather than the core collapse of a massive star. Tycho's supernova remnant, the result of a supernova observed by the Danish astronomer Tycho Brahe in 1572 and widely noted across Europe, is another extensively studied remnant that also appears to be of Type Ia origin. Kepler's supernova remnant, from the 1604 event observed by Johannes Kepler and visible in daylight for 3 weeks, is the last supernova to be observed with the naked eye within our own Milky Way galaxy, a record that stands more than 4 centuries later. Section 13. The cycle of death and birth. The death of a star is never simply a death. Every stellar death is also a contribution to future stars, future planetary systems, future chemistry. The universe has no mechanism for permanent waste. Everything that leaves a dying star and enters the interstellar medium eventually participates in the formation of something new. This is not an analogy or a metaphor. It is the observable process of galactic chemical evolution playing out over billions of years. Supernova shockwaves propagate through the interstellar medium at velocities ranging from thousands to tens of thousands of kilometers per second, sweeping up and compressing the gas and dust they encounter. When such a shockwave strikes a molecular cloud, the cold, dense region where new stars form, the compression can push dense cores of the cloud past the gene's mass threshold, the critical mass above which a gas cloud's self-gravity overwhelms its internal thermal pressure. Collapse begins. New protostars form. Dying stars trigger the birth of new stars in a cascading sequence across millions of years. This triggered star formation has been observed in multiple environments throughout the Milky Way and nearby galaxies. The massive OB associations, clusters of hot, luminous, short-lived stars found in the spiral arms of our galaxy, often show compelling evidence for sequential star formation moving through a parent molecular cloud. Different regions of the cloud contain stellar populations of different ages, suggesting that each generation of massive stars was born, lived its short life, died in a supernova, and triggered the birth of the next generation in the adjacent undisturbed cloud. The process cascades through the cloud over tens of millions of years, leaving behind a complex assemblage of clusters and associations of progressively older stellar populations. Our own solar system may carry direct isotopic evidence of triggered formation. The most primitive objects in the solar system, calcium-aluminum-rich inclusions in carbonaceous chondrite meteorites, contain elevated abundances of the decay products of short-lived radioactive isotopes, including those of aluminum-26, which has a half-life of only 730,000 years, and iron-60, with a half-life of 2.6 million years. These isotopes are produced in supernovae and in the winds of massive stars. Their elevated presence in early solar system material implies that a nearby massive star contributed freshly synthesized radioactive material to the pre-solar cloud very shortly before or during solar system formation. The most natural interpretation is that the shockwave from a nearby supernova both triggered the collapse of the pre-solar cloud and simultaneously seeded it with fresh nucleosynthetic products. Our solar system may owe its very existence to the death of a massive star 4.6 billion years ago. As each successive generation of stars forms from increasingly enriched interstellar gas, the chemical complexity of stellar and planetary systems grows. The first generation of stars formed from essentially pure hydrogen and helium. Their deaths created the conditions for second-generation stars with traces of carbon, oxygen, and other elements. Third-generation stars incorporated the outputs of 2 previous generations, and so it has continued, through many cycles of birth, burning, and death, until the stars forming today inherit the accumulated chemical complexity of all the stellar generations that preceded them over the full history of the galaxy. The stars forming in molecular clouds today, in the Orion Molecular Cloud, the Eagle Nebula, the Carina Nebula, and thousands of similar regions scattered through the Milky Way, form from gas, carrying the outputs of billions of years of stellar nucleosynthesis and stellar death. The rocky planets forming around them start with more heavy elements than Earth had available at its formation 4.6 billion years ago. If conditions are right on those planets, the greater availability of heavy elements may make complex chemistry and complex life more probable than it was for Earth. The universe is directional in a chemical sense. It started from hydrogen and helium simplicity and moves, via the birth and death of stars, toward increasing chemical complexity. Each generation of stars builds a slightly richer chemical environment for the next. The process is not permanent, since gas supplies in galaxies are finite and will eventually be exhausted. But on the timescale of the current universe, the death of stars is the engine of increasing chemical richness. There is a perspective shift available to anyone who follows this entire story from beginning to end, and it is not a minor adjustment. It changes the meaning of the physical world around you, the meaning of the atoms in your body, and the meaning of the sky above you on any night you care to look up. The iron flowing through your blood right now, in every hemoglobin molecule carrying oxygen from your lungs to every cell, was forged in the core of a massive star. That star lived for millions of years, burning its nuclear fuel in sequence, from hydrogen through helium and carbon and oxygen and silicon, building an iron core over thousands of years of silicon burning. Then in less than a second its core collapsed, and a shockwave tore outward through the stellar envelope, and the star exploded, and the iron that had been locked in the stellar core was flung outward at thousands of kilometers per second across the surrounding space. Over millions of years, that iron mixed into the diffuse interstellar gas of the galaxy. Over further millions of years, it was swept up into the molecular cloud that was collapsing to form our solar system. It accreted into planetesimals and eventually into Earth, was processed through billions of years of geological cycles, ocean chemistry, and biological evolution, and eventually ended up in a molecule inside a cell inside you. The journey from the core of a massive star to your blood took approximately 10 billion years. The calcium in your skeleton was forged in the oxygen-burning stage of a massive star. The oxygen cycling through your lungs with every breath was produced in stellar nuclear burning and distributed by stellar death. The carbon forming the molecular backbone of every organic molecule in you, in your DNA, in the proteins mediating every biochemical reaction in every cell you contain, was assembled by helium burning in stars billions of years ago and distributed through stellar winds and planetary nebulae. The nitrogen in your genetic code, in every amino acid in every protein, was processed through stellar hydrogen-burning zones. The phosphorus in the ATP powering your cellular metabolism this very moment was forged in stellar burning and scattered by a stellar death. If you are wearing gold right now, a wedding ring, a chain, a watch, a piece of jewelry of any kind, those gold atoms were assembled in a kilonova. The collision of two neutron stars, probably billions of years ago, assembled those nuclei from the intense neutron flux in the merger debris, sprayed them into space in the kilonova ejector, mixed them into the interstellar medium, swept them into the pre-solar cloud, and eventually deposited them in the ore deposits that human beings later mined. Those two neutron stars themselves only existed because massive stars had previously died in core collapse supernovae. Every gold atom on Earth required at minimum 2 separate stellar deaths to create it. Somewhere in the Milky Way right now, unknown to any astronomer, a massive star's iron core is approaching the Chandrasekhar limit. Silicon burning is adding the last grams of iron to a core that cannot hold itself much longer. When it reaches the limit, the collapse will begin, and in less than a second, a neutron star will exist where a stellar core was, and a shockwave will be propagating outward through the star. Hours later, the star will begin to brighten. Neutrino detectors on Earth, if the star is close enough, will catch the signal first, before any telescope sees anything change in the sky. The Supernova Early Warning System network will alert astronomers worldwide. Every available telescope will swing to the location, and the data gathered will advance our understanding of nuclear physics, neutrino physics, gravitational wave astronomy, and the origin of the elements more than any previous observation. That is what awaits the next Milky Way supernova. And the Milky Way is statistically overdue for one, based on historical rates. It could happen tomorrow, or it could be centuries away. But it will happen, because massive stars are still being born in the spiral arms of our galaxy right now, and massive stars always die violently. Betelgeuse will explode tens of thousands to hundreds of thousands of years from now. When it does, its shockwave will propagate outward through the surrounding interstellar medium, compressing gas clouds, potentially triggering new star formation. The elements forged inside Betelgeuse over its several million-year life, carbon, oxygen, and everything heavier, will be distributed across light-years of space. Some of those atoms will eventually find their way into new molecular clouds, into new protostars, into new planets. And on some of those planets, the chemistry enabled by the elements from Betelgeuse's death may do something remarkable over billions of years. That is not science fiction. That is the stellar life cycle applied forward in time. It has been happening continuously since the first massive stars died more than 13 billion years ago. It is happening right now in galaxies across the observable universe. Every galaxy you see in a deep field image from the Hubble or Webb space telescopes contains hundreds of billions of stars, and many of those stars are somewhere in the process of stellar death right now. Planetary nebulae are expanding outward from dying sun-like stars. Supernovae are flashing off in distant galaxies. Neutron stars are spiraling together over millions of years toward kilonovae that will forge gold and platinum and uranium. All of it connects back to the fact that you exist. Without stellar death, without the supernovae that distributed oxygen and iron and silicon, without the neutron star mergers that produced gold and uranium, without the quiet planetary nebulae that recycled carbon and nitrogen, the universe would be a vastly simpler and emptier place, a place of hydrogen and helium and nothing more. Not a place where rocky planets could form, not a place where oceans could exist, not a place where life was possible. The universe built you out of dead stars. It took around 10 billion years of stellar birth, nuclear burning, and stellar death to assemble the chemical palette from which you were eventually made. The timescale is staggering, but the mechanism is clear, the evidence is overwhelming, and the implication carries a weight that nothing else quite matches. Every breath you take contains atoms that have been through stars. Every heartbeat pumps iron forged in a stellar core. Every thought you have is processed in biological machinery, built from molecules that passed through stellar interiors billions of years before Earth existed. You are carrying ancient stellar history inside you, right now, in every atom. The sky you look at tonight is full of stars still doing what previous stars did to make you, forging elements, building complexity, moving eventually toward deaths that will distribute that complexity outward into the galaxy, seeding future clouds, future stars, future planets, future chemistry, future everything. That is not a small thing to carry with you when you look up. One aspect of massive stellar evolution that does not always receive adequate attention is how dramatically these stars change in the years, centuries, and millennia before their cores collapse. Long before the final silicon burning stage, massive stars are shedding mass at prodigious rates through powerful stellar winds driven by radiation pressure on metal ions in the stellar atmosphere. This mass loss is not just incidental to the star's evolution. It fundamentally alters the star's structure, its final mass at death, the type of supernova it produces, and the appearance of the supernova remnant for years and decades after the explosion. The winds of massive stars carry momentum imparted by photons from the star's intense radiation field, scattering off metal ions in the outer layers. Because the radiation field of a very luminous star is so intense, the momentum transferred can be sufficient to accelerate the outer atmosphere to velocities of hundreds or thousands of kilometers per second, far in excess of the star's escape velocity. The stellar atmosphere essentially evaporates under its own photon pressure. For the most luminous massive stars, the wind mass loss rates can reach 10 to the power of -4 solar masses per year or more, meaning the star can lose a significant fraction of its total mass over its main sequence lifetime before it ever gets to the red supergiant phase. This radiation-driven wind mass loss depends strongly on the metallicity of the star, the abundance of elements heavier than helium whose spectral lines efficiently scatter photons. A metal-rich star loses mass much faster than a metal-poor star of the same luminosity, because it has more scattering lines available. This has profound consequences for the expected stellar death products at different cosmic epochs. In the early universe, where stellar metallicities were very low because heavy elements had not yet been built up by previous stellar generations, massive stars retained more of their mass to the end of their lives and likely formed more massive compact remnants. The first generation of massive stars may have produced very massive black holes through this mechanism, and some of the merging black holes detected by LIGO with masses of 50 to 80 solar masses may be remnants of these low metallicity first-generation massive stars. In the last years of a massive star's life, the mass loss can become episodic and dramatically more intense than during the steady stellar wind phase. Luminous blue variables, a class of massive stars known for giant eruptions that can expel solar masses of material in brief events, are thought to represent massive stars in an unstable transitional phase between the main sequence and the red supergiant or Wolf-Rayet stage. The 1840s eruption of Eta Carinae, a massive star about 7,500 light-years away that temporarily became one of the brightest stars in the southern sky while expelling roughly 10 to 20 solar masses of material, is one of the most dramatic recorded examples of this kind of pre-supernova instability. Eta Carinae survived that eruption but is expected to explode as a supernova at some point in the astronomically near future, and when it does, its blast wave will collide with the material expelled in the 1840s eruption, producing a supernova interacting with its own pre-ejected shell in what astronomers call a Type 1n supernova. The shells of material ejected before a supernova, whether in steady winds or in episodic giant eruptions, can produce spectacular spectral and photometric signatures when the supernova blast wave overtakes them. These interacting supernovae, where the blast wave runs into dense circumstellar material shed by the progenitor, can be far brighter and longer lasting than ordinary supernovae, because the kinetic energy of the blast wave is converted to light by the interaction with the circumstellar material. Some of the most luminous supernovae ever observed, called superluminous supernovae, may derive their extreme brightness partly from this kind of circumstellar interaction, suggesting that their progenitors experienced dramatic pre-explosion mass loss episodes in the years to decades before the core collapsed. It is worth stepping back from the individual stories of stellar death and taking stock of what the universe has accumulated over its 13.8 billion-year history, an enormous population of stellar remnants, the dead and cooling bodies of generations of stars that lived and died before the current ones. White dwarfs, neutron stars, and black holes are not rare exotic objects. They are the normal, expected endpoints of stellar evolution, and the Milky Way is full of them. White dwarfs are the most common remnant type because the vast majority of all stars will end their lives as white dwarfs. The Milky Way contains an estimated 10 billion or more white dwarfs, though most are too faint to be individually detected at large distances. The local sample within a few hundred light-years is well characterized and shows a distribution of white dwarf temperatures and luminosities consistent with cooling models covering a range of ages from freshly formed hot white dwarfs to ancient, dim white dwarfs that formed billions of years ago. The oldest, coolest white dwarfs in the Milky Way carry information about the age of the galaxy and the history of star formation, because their cooling times, calculated from their luminosities and masses, give a lower limit on the age of the stellar population that produced them. Neutron stars are less common than white dwarfs, because they only form from massive stars that constitute a small fraction of the total stellar population. The Milky Way contains an estimated 100 million to a billion neutron stars, though only a few thousand are currently detectable as pulsars, because the geometry must be right for the pulsar beam to sweep past Earth, and because older neutron stars spin too slowly, and their beams fade too much to be detectable. Neutron stars that are not detected as pulsars, often called central compact objects or isolated neutron stars depending on context, can sometimes be detected through their X-ray emission as they cool, but most of the Milky Way's neutron stars are completely invisible to current instruments. Stellar black holes are even less numerous than neutron stars, forming only from the most massive progenitors, but the Milky Way is thought to contain several 100 million stellar black holes. Essentially, none of these are individually detectable by current methods, unless they are in binary systems with detectable companion stars, or unless they are currently merging with other compact objects. The vast majority of stellar black holes are dark, silent, and invisible, scattered through the galaxy, gravitationally interacting with their surroundings, but producing no detectable electromagnetic radiation. LIGO is gradually building up a catalogue of merging black holes, but these represent only the small fraction that happen to be in merging binaries during the current observational window. Together, white dwarfs, neutron stars, and black holes represent the accumulated stellar graveyard of the Milky Way, the compressed, cooled, and dark remnants of every star more massive than about half a solar mass that has ever lived and died in our galaxy. They carry within them the record of every nuclear burning stage that ever occurred in every progenitor star, preserved in their compositions, masses, and structures. They orbit the galaxy on orbits that remember the supernovae that kick them to their current positions. They occasionally interact with companions in binary systems, producing novae, millisecond pulsars, and Type 1a supernovae that light up the galaxy. And now, through gravitational wave detectors, they speak to us directly when they collide, revealing their masses, spins, and internal structures through the precise waveforms of the gravitational radiation they emit. The stellar graveyard is not silent. It is, in ways we have only recently learned to hear, one of the richest sources of information about the history of the universe available to us. It is worth stepping back and appreciating how much of what is described in this video was entirely unknown a century ago, and how rapidly the field continues to develop. In 1920, the source of the sun's energy was genuinely unknown. The most favored hypothesis was gravitational contraction, the Kelvin-Helmholtz mechanism, but calculations showed this could sustain the sun's luminosity for only about 20 million years, far too short to be consistent with geological evidence for an ancient Earth. The discovery of nuclear fusion in the 1930s and its application to stellar interiors by Hans Bethe and others finally resolved this question and established that stellar lifetimes could indeed be measured in billions of years. Neutron stars were predicted theoretically by Walter Baade and Fritz Zwicky in 1934, just 2 years after the discovery of the neutron itself, on the basis that core collapse supernovae might produce compact stellar remnants. The prediction was so far ahead of observational capability that neutron stars remained theoretical objects for more than 30 years, until Jocelyn Bell Burnell's discovery of the first pulsar in 1967 provided the observational confirmation. Black holes, though implicit in Einstein's 1915 general relativity equations, were for decades considered physically unrealistic curiosities by many physicists, including Einstein himself. Observational confirmation of their existence as real astrophysical objects came only in the 1970s and 1980s through X-ray binary observations, and direct confirmation through gravitational waves came only in 2015 with LIGO's first detection. Nucleosynthesis, the process by which stars build the elements, was understood in outline by the 1950s through the B2FH paper and related work, but the specific site of the R process remained unknown for another 6 decades until the GW170817 kilonova observation in 2017 provided the first direct evidence that neutron star mergers are a major R process site. And many fundamental questions remain open. We do not know the precise mechanism by which core collapse supernovae produce successful explosions. We do not know what matter looks like at the densities found in neutron star cores. We do not know whether there are additional R process sites beyond neutron star mergers. We do not know how the mass gap between neutron stars and black holes arises. We do not know exactly how the mass and metallicity of a progenitor star determines whether it produces a neutron star or a black hole. Every one of these open questions is being attacked by current research, using new generations of neutrino detectors, gravitational wave observatories with improving sensitivity, next-generation X-ray space telescopes, high-resolution radio telescope arrays, and increasingly sophisticated computer simulations of stellar explosions. The era we are living in, with gravitational wave astronomy now mature and multi-messenger observations becoming routine, is arguably the most rapidly advancing period in the history of astrophysics. The discoveries of the last decade have transformed our understanding, and the discoveries of the next decade promise to transform it again. Let us do something specific. Let us trace the actual atoms in a human body back to their stellar origins, element by element, because the exercise makes the connection between stellar death and human existence concrete in a way that abstract descriptions cannot quite achieve. Hydrogen is the most abundant atom in the human body by number, making up about 60% of all atoms in your body. Almost all of it, more than 99.9%, was produced in the Big Bang itself, more than 13 billion years ago, and has been cycling through various forms ever since. Nebulae, stars, stellar winds, interstellar gas, molecular clouds, planets, oceans, and living things. The hydrogen in your body is among the oldest matter in existence. Oxygen is the most abundant element in the human body by mass, making up roughly 65% of your total mass. Oxygen is produced primarily in stellar helium burning through the triple alpha process and the subsequent capture of another helium nucleus by carbon. It is distributed by stellar death, the stellar winds and planetary nebulae of dying sun-like stars, and the supernova explosions of massive stars. Every oxygen atom in your body passed through at least one stellar interior, was expelled in some form of stellar death, and eventually found its way into the pre-solar cloud, and then into Earth's chemistry and your biology. Carbon is the second most abundant element in your body by number of atoms, and the foundation of all organic chemistry. Like oxygen, it is produced primarily in stellar helium burning. Carbon atoms in your body were forged in the triple alpha process inside stars that lived and died before the sun formed, shed into space through stellar winds or planetary nebulae, mixed into the interstellar medium, and incorporated into the pre-solar cloud. The specific carbon atoms in any given molecule of your DNA have a history spanning billions of years, and at minimum, one stellar interior. Nitrogen makes up about 3% of human body mass and is essential for amino acids and nucleotides. Nitrogen is produced primarily in the CNO cycle of hydrogen burning in stellar interiors, and also in the helium-burning shells of asymptotic giant branch stars, where dredge-up events mix CNO-processed material to the surface. The nitrogen in your body was processed through stellar interiors, expelled in stellar winds, and cycled through the interstellar medium before being incorporated into Earth's atmosphere and eventually into biological molecules. Calcium, making up about 1.5% of human body mass and found almost entirely in bones and teeth, is produced in the oxygen-burning stage of massive stars, at temperatures around 2 billion degrees in the oxygen-burning shell. The calcium in your skeleton was forged in the interior of a massive star that later exploded, distributing the calcium into the interstellar medium, where it eventually became part of the solar nebula and then part of Earth's rocky chemistry. Iron, making up about 0.006% of human body mass, but carrying roughly 0.4% of the oxygen in your blood through hemoglobin, is the terminal product of massive stellar nuclear burning, produced in the silicon burning stage and in the explosive nucleosynthesis of core collapse supernovae. The iron in your blood was the last element forged in a stellar core before that core collapsed and the star exploded. In a very direct sense, the iron in your hemoglobin was born in the death of a star. Phosphorus, essential for ATP and DNA and making up about 1% of body mass, is produced in oxygen-burning and neon-burning stages in massive stars. Sulfur, present in cysteine and methionine amino acids and in enzyme active sites, is also an oxygen-burning product. Potassium and sodium, which maintain the electrical potential across cell membranes and make neural signaling possible, are produced in the oxygen-burning stage of massive stars. The nerve impulse that allowed you to start reading this sentence originated in an electrochemical gradient, maintained by atoms forged in stellar oxygen-burning zones billions of years ago. Zinc and selenium, trace elements essential for numerous enzymes, are produced by the S process in asymptotic giant branch stars. Iodine, essential for thyroid hormones, is produced by the R process in neutron star mergers. The iron in your blood and the iodine in your thyroid gland have completely different stellar origins. The iron from a supernova, the iodine from a kilonova. Different stellar deaths contributed different atoms to different biological functions in your body right now. You are not just abstractly made of star stuff. You are an intricate mixture of products from multiple different types of stellar death, assembled over billions of years of galactic chemical evolution into a configuration complex enough to think about where it came from. The next time you stand outside on a clear night and look up at the stars, you are seeing the universe in the middle of its ongoing process of stellar death and rebirth simultaneously. The bright blue-white stars you can see, stars like Rigel in Orion or Spica in Virgo, are massive main-sequence stars burning their hydrogen so intensely that they will exhaust it in only a few million years. In astronomical terms, they are almost finished. Some of them have already advanced into their post-main sequence phases and will die in core collapse supernovae within a geologically brief period. By the time multicellular life first appeared on Earth, these particular stars will not exist. Their deaths have already been set in motion, and the clock is running. The fainter yellow stars you might notice, similar in color to the Sun, are Sun-like main sequence stars in the long, stable middle of their lives, billions of years from significant change. They represent the current steady state of stellar existence, hydrostatic equilibrium maintained, hydrogen burning quietly at their cores. The distinctly orange-red stars visible to the naked eye, stars like Arcturus and Aldebaran, and of course, Betelgeuse, are stars in their evolved phases, red giants and red supergiants that have exhausted their core hydrogen and expanded dramatically. They are dying, in the slow or fast stellar sense, and their deaths will produce either planetary nebulae and white dwarfs or supernovae and neutron stars, depending on their masses. Embedded in the Milky Way band, visible on a truly dark night, are the young star-forming regions where new stars are forming right now. The Orion Nebula, visible to the naked eye as a fuzzy spot in Orion's sword, is the nearest major stellar nursery to Earth, about 1,300 light-years away, where massive clouds of gas are collapsing under gravity to form hundreds of new stars. The brilliant trapezium of hot young stars at the center of the Orion Nebula formed only about 100,000 years ago and are already ionizing the surrounding gas with their intense ultraviolet radiation. They will live only a few million years before dying as supernovae. The young stars in Orion were not born from pristine Big Bang hydrogen and helium. They formed from gas already enriched by the deaths of many previous stellar generations, carrying within them the chemical legacy of all the stars that lived and died before them. When those young Orion stars die in supernovae millions of years from now, their explosions will enrich the surrounding interstellar medium further and may trigger yet another generation of star formation in the molecular clouds beyond the current nebula. The sky above you is not a static display. It is a long-running process, a continuous cycle of stellar birth, nuclear burning, and stellar death that has been running for more than 13 billion years and will continue for trillions more. You are seeing one moment in that process, a snapshot taken at the particular cosmic instant that happens to coincide with your existence on a rocky planet orbiting a middle-aged star in an ordinary spiral galaxy. That rocky planet, that star, and everything on it and in it, is itself a product of earlier moments in the same process. The universe built you, and the universe is still building, still burning, still dying and being reborn, in every direction you look. One of the hardest things about stellar astrophysics is the sheer range of timescales involved, and the way this range makes it impossible to hold the full story in any single human-scale frame of reference. Consider, the iron core of a massive star collapses in a quarter of a second. The ensuing supernova brightens over days to weeks and fades over months. The expanding remnant is observable for thousands of years. The neutron star left behind will cool over millions of years, and its pulsar beam will sweep through space for tens of millions of years before the star spins down too much to be detectable. The white dwarf, formed from a sun-like star, will cool for trillions of years. The black hole, formed from a massive star, will persist for 10 to the power of 74 years before Hawking radiation evaporates it. These timescales span more than 80 orders of magnitude. No human intuition can bridge that range, but what is worth holding on to is that all these timescales are happening simultaneously, right now, across the universe. The quarter-second core collapse of some massive star is happening somewhere in the universe as you read this. The expanding remnant of SN 1987A has been evolving for nearly 4 decades and is still changing. The Crab pulsar has been spinning for 970 years since the 1054 supernova and will continue spinning for millions more. Sirius B has been cooling for several 100 million years since its progenitor died. And somewhere in the universe, black holes formed in the first billion years of cosmic history are still sitting in the cores of ancient galaxies, having absorbed the deaths of countless stars over the full history of the observable universe. The universe does not operate on human timescales. It never has. The processes that produced the atoms in your body began billions of years before your species existed, will continue for billions of years after it is gone, and have been running continuously throughout. What is remarkable is not that these processes are happening. What is remarkable is that, at this particular moment in cosmic history, there exist creatures on at least one rocky planet who have figured out what is happening and why. That is, in the full context of stellar evolution and galactic chemical history, an extraordinary thing. The next time Orion rises in the winter sky and you see the orange-red glow of Betelgeuse at its shoulder, you are looking at a star that will one day explode and distribute its contents across the surrounding galaxy. Some of what Betelgeuse is made of will become part of new stars and new planets. Some of those planets, billions of years from now, may have atmospheres and oceans. Some of those oceans may develop chemistry complex enough to constitute life, and some of that life, further billions of years beyond that, may look up at whatever stars burn in their sky and ask the same questions we are asking now. Where did we come from? And what are those lights above us? And what will they become? The answer to all of those questions, for us and for any other beings in the universe asking them, runs through the same place, the deaths of stars. We are living at an extraordinary moment in the history of stellar astrophysics. The tools available to study stellar death have never been more powerful, and the discoveries of the last decade have opened entirely new windows onto processes that were previously theoretical or unobservable. The next decade or two promises to be at least as rich. Gravitational wave astronomy is still in its infancy. LIGO and Virgo have completed several observing runs and accumulated dozens of confirmed detections of compact object mergers. But the planned next generation of ground-based gravitational wave detectors, including the Einstein telescope in Europe and Cosmic Explorer in the United States, will be sensitive enough to detect stellar mass black hole mergers throughout the observable universe and neutron star mergers to distances of billions of light years. Instead of a few dozen detections per observing run, these detectors will accumulate thousands of detections per year, turning gravitational wave astronomy into a statistical science capable of measuring the rates and properties of compact object mergers with the kind of precision that changes our understanding of stellar evolution, nucleosynthesis, and cosmology simultaneously. The Rubin Observatory, also known as the Legacy Survey of Space and Time Facility, is scheduled to begin full operations in the mid-2020s and will survey the entire accessible sky repeatedly every few nights for a decade, discovering hundreds of thousands of supernovae across billions of light-years of cosmic volume. This survey will provide the most complete statistical census ever assembled of supernova rates, types, environments, and progenitors, addressing fundamental questions about which stars produce which types of supernovae and how the supernova rate has evolved with cosmic time. New and upgraded neutrino detectors, including the Hyper Kamiokande facility in Japan and the Deep Underground Neutrino experiment in the United States, will be sensitive enough to detect the neutrino burst from a core collapse supernova anywhere in the Milky Way and in the Magellanic Clouds with far greater statistical precision than SN 1987A provided. They will also be sensitive to pre-supernova neutrino emission from the final nuclear burning stages of nearby massive stars, potentially providing several hours of warning before the stellar collapse occurs, allowing the astronomical community to observe the stellar surface in the final hours before the explosion begins. The Roman Space Telescope, formerly known as WFIRST, will have a field of view 100 times larger than the Hubble Space Telescope's Wide Field Camera 3, while maintaining similar image quality, enabling surveys for supernovae and their optical transient cousins across enormous volumes of the universe. Combined with the James Webb Space Telescope's extraordinary infrared sensitivity, the Roman telescope will allow detailed studies of supernovae in distant galaxies, tracking how their properties change with cosmic time and environment. And the next nearby supernova, whenever it comes, will be the pivotal event of a generation, whether it is Betelgeuse in tens of thousands of years, or some unknown massive star anywhere in the Milky Way that collapses tomorrow. The event will generate more multi-messenger data than all previous supernova observations combined. Neutrino detectors will catch the burst with unprecedented statistics. Gravitational wave detectors will search for the asymmetric collapse signal. Every optical, infrared, radio, and X-ray telescope available will observe the event continuously from the first moment of warning. And for the first time, we may be able to answer definitively how the explosion happens, how the neutron star forms, how the elements are distributed in the ejector, and what the remnant structure looks like in its earliest moments. The science of stellar death is not finished. It is accelerating. Every generation of astronomers discovers that what the previous generation thought was a complete picture was actually only a partial view, and every new instrument opens unexpected vistas. The deaths of stars will continue to surprise us, illuminate us, and connect us to the full 13.8 billion year history of a universe that has been assembling complexity from simplicity since the first moments after its beginning. And somewhere in all that complexity, assembled from the deaths of ancient stars and carried through 4.5 billion years of planetary and biological history, are the people asking the questions. The fact that asking the questions is possible at all is, when you think about it properly, the most extraordinary product of stellar death of all.